Hello guys, and welcome back to my channel Civil Construction and Tutor. And in this video we will be designing a steel warehouse considering portal frames and using roof and wall bracing structures. So for this we are considering this architectural drawing. So we have portal frames at a spacing of 6.3 meters, and this is the elevation view. So this is the front view and these are the side elevations. So before starting we should know a bit idea about the portal frame design. So as I said, we'll be considering the portal frame in this direction. So this elevation gives an idea about the portal frame. So we'll have a column here, over here, and this being the rafters, or we can say beam. So this is the portal frame action, and that is how the lateral stability along this direction is achieved. And along this direction, if you see here, so this is an I section, this is the major axis, and this being along the minor axis. So basically for that we'll be considering the bracings. So if you see here, this can give you idea about the portal frame. So this is a portal frame, and whatever the wind load comes from this direction, suppose this cladding, the load acting on this cladding gets transferred to this frame, and with the portal frame action the load gets to the foundation. However, first for the other direction, that is along, if the wind blows from this direction, these claddings are subjected to the wind action, and that transfers load to these columns. But we do not have any specific structural element along this direction, and in that place the bracing comes into action. If you see here, we have bracings here as well. So you can see here, these are the bracings. We also have bracing in the roof. So now let us try to understand how portal frame works. For example, this is the portal frame, and this portal frame, for the lateral direction, the tributary area is this half of this span and half of this span, and this much of load is transferred, is subjected to this portal frame, and with the portal frame action the load gets transferred to the footing. But for the other direction, when the wind blows from this direction, we don't have structural element to take the load, that is for the structural stability. So if there is no any structural component to take this load, structure will collapse. So if there is no any bracings, and with the structure, as we know, if this is a portal frame in this direction, along the minor axis the capacity of the section is quite low, and it will fall down or it will collapse. So for that the bracing comes into action. Let us say we have a bracing at this point. So this is the bracing. We have a nodal connection, that is the strut, or we can say purlin, at this point. So that comes into action. So if the point load gets transferred along this direction, let us see here, and we also have a bracing at this point. Let us see in a plan view for this bracing only. So this, and we have a point load at this point. See, these bracings are generally provided as an angle section or a rod, simple rod. Let us consider a rod, and the rod being simply capable of taking tension only. So a rod, you can simply consider a reinforcement type rod, 16 mm rod or 20 mm rod, that is not capable of taking the compression, that is only capable of taking tension. So this goes into this strut, right? And this strut, now if we see here, this is a purlin, and it is subjected to a wind load as well. And due to the wind load, considering this as a simply supported connection, so with the wind load it has a moment, and at the same time, due to the wind load, lateral wind load, it is also subjected to a axial force. Now we have to consider the combined action. So the frame, this purlin cannot be designed just for bending moment, it has to be considered for the axial force as well. So let us say this section has an axial capacity of fd, right? Design axial capacity. Now due to the bending moment, this axial capacity is reduced to a certain limit. So whatever the axial capacity that strut have now gets reduced, so we have to consider that as well. So that is one check that we have to consider while designing the purlins for our portal frame. So that is combined action. Now let us come back to this point. So this structure now is subjected to a wind load. Now its get deformed to this direction, right? Now if we see this bracing now comes into tension, so this is capable of taking the tension. So whatever the tension force will be here in this direction comes into play, and that force comes back to this point and gets distributed to this strap and comes back to the footing. So this is how the bracing works. So the force is applied to a node, gets transferred through the strut, and with the nodal force resolve. So we are just resolving the force. That force comes back to this bracing, and again at this point the force gets distributed to the other bracing and finally comes down to the footing. So whatever the force will be exerted on this face directly comes down to the footing due to the bracing action. So that is how the lateral stability along this direction is considered. So till now, some major points to be considered. One is the direction of the column section for the portal frame action. Secondly, we have to consider the struts for a combined action, that is for the bending moment due to the upward wind load and axial force due to the lateral wind load. Now we might see bracing in this direction as well, that is along the portal frame as well. So the basic idea of providing this bracing in this direction as well. So if you see here, it is termed as mullions. So this connection are simply pin joint connection here. We cannot we generally do not provide a moment connection. And the direction, if you see here, these are provided along this direction. The major axis is provided along the direction or the wind direction. So considering the bracing action, we can reduce the section size here. Even if we see here, we have C2 and C1. So basically with the inclusion of the bracing in this direction, we can reduce the section size. So that is one advantage, having these columns at mid span, which are basically termed as mullions. So we can take that advantage of the bracing, and again the lateral load comes to this point and goes through this raptor and comes back with the bracing action to the footing. So this is an advantage of providing bracing. The other thing that we have to consider is, so we have transferred the lateral force of this face directly to the footing. So the connection that we provide here with the bolt action, the design must be sufficient to take that horizontal load which is transferred to this footing. And also if we see in the plan view for this wall, so if we see this frame, so we have bracing here, right? And when we have an axial force, so that goes in this direction, and this bracing goes into tension or compression, whatever. So that depends upon the type of the section you provide here, whether it is an strap, whether it is an rod, or it is an hollow section, or it is an angle section. So whatever the section is capable of, let us assume it has a rod bracing, so that is capable of tension only. So if you see here, it goes under tension. Now in this point, at this point, we'll have a force resolution. So one of the force will be an uplift force and the other force will be horizontal force. So this connection shall be capable of taking both of them, that is uplift force as well as the shear force, shear action for this bolt connection. So now let us go to the design part. So I hope you guys know how to use ETABS. So I have uploaded a many of videos for the ETABS designing. So I'll just go quickly to the design part. So starting with the modify grid part. So let us see the grid arrangement. 1 2 3 4, okay. And also we have to make sure the story height, architectural drawing, so elevation, so eve height is 5500 and 700 is the apex height, so 5.5. Elevation view for this one, so let us select any one of it. So quick draw, and here we have steel column, okay. And whatever the section, let us select this one. So we have here one column, here as well. So firstly I'll just make the portal frame, and for the beam also let us select ISMB 250. We can change the section whenever we want. So this is exactly the portal frame, right? And let us select one of the section. So depending upon what your reason is, for now let me select as IS Indian standard. And for the material, what I can do is simply consider Indian and FE 250 section, frame section, and coming back to import new properties, I section. So for now I'll be considering IS MB section, that is medium section. And from now let me take IS MB 450. Okay, and I'll just provide all of them as IS MB 450. So in the exterior view you can see the orientation. So it is not the orientation that we are looking for. So if we see in the plan view, we want this frame, right, the I section, to face the, that is the major axis along Y. So assign, and here we can just go to local axis and turn that by 90 degree. So okay, right, now let us go to the 3D view and we'll simply copy all of them and replicate them. So from here to here, and we have 1 2 3 4 5 6. So number 6, apply. Okay, and in this point we also have mullions, so it's a bit trickier to draw that because we don't have a intersection point here. So what we can do is using the grid intersection for this two, edit frames, divide frames here at intersection with visible grid lines. Okay, now let us draw. For these mullions, this direction is okay because we are considering the strong axis for this direction. So we are done with the portal frame, and the base will be a pin joint as well. Position of the struts. So let us take 150 by 106 RHS as an strut for now. We'll check whether it is sufficient or not. It is subjected to a lateral load and a bending moment as well. So the purlin undergoes a combined action. Now we can just divide this using the same function, that is visible grid line, right? And I have calculated the load that will be subjected to these frames, whatever the section here. So these central raptors, let me define one load here. So we have wind load, so I'm just taking that one. The effective tributary area for the central raptor is greater than that of this end raptor, so it is subjected to half of this area only. So assign frame load distributed, and this being wind load. So I have computed that load, and that will be along the local axis 2 for the frame, and it is 10.2 kilonewton. So I have already uploaded a video for calculation of the wind load, you can check that. So for now it will make the video longer, so just taking the wind load whatever that I have calculated. So along the wind direction, that is the local axis of these frames, and for the end raptors it will be half of the load. So basically this loading that I have calculated is for a cyclonic region. It is quite, so it is quite high because I have calculated the wind load for wind speed of 66 meter per second, and also I am just assuming same coefficient throughout the length, which is not the case. Hence the section size might not be sufficient that I have provided, so you have to cope up with that one while you design your. And this wind load is on basis of whatever the load that blows from here, right, and from this direction it will be different. Now let us take these columns for the wind load. So again the same concept, these end columns will be subjected to a lesser load, while the central columns will be subjected to higher load. So the wind direction will be in this direction, so the frame, the wind load will be in this direction as well. And for this end portal frame, this will undergo suction effect, so it is also subjected to the same load. And regarding these conditions, that is equal load on this face and equal load on that face being symmetrical in nature, so we'll just consider this load only. Now we have this loading arrangement. And the other thing we have to consider, as I said, these will have a simple pin joint connection, right? So all these struts, and also these mullions, so we'll do that later on. So assign frame, and here we have release partial fixity, so moment released connection. And this also applies with this one. Yep, so this connection. Okay, now let us run the model. So you can see that the structure is unstable, right? Now let us introduce the bracings. So now let us provide a bracing for these structures. So for that, let us consider a angle section. So here we have steel angle section, and whatever the requirement will be. So let me just draw a bracing to make it clear about it. Now let us see the extruded view, so we can get an idea about the bracing, right? Now we have to provide the releases for this one. So simply select and then go to properties, frame sections. So for all the angle sections, we'll just uh, provide a release for the moment. Now let us see if the structure is stable. Now let us run. So you can see now the structure is stable, right? So this is how the lateral stability is achieved with the bracings. Now let us go for the, so now let us see the frame results. So going to this member force diagram, starting with the wind load, and we have moment 3 3. So also check the local axis. So this for the frame. So R, that is red, green and blue. So R is the local axis 1, G, that is green local axis 2 and 3. So we have to check this. And now let us see the moment. So moment 3 3. So moment about major axis. So we can see whatever the moment there is, so it is okay with this one, unless the moment about the minor axis is very much high. That is okay, because the moment carrying capacity along the minor axis will be surely small as compared to the major axis. And similarly, so in this direction as well, so we don't have that much of the moment that is about the minor axis, so it's about 17 kilonewton, so that must be capable of taking. So we have to take that into the consideration while designing the selecting the section size. Similarly, axial load. So see, these bracing members are subjected to, that is the axial force. The other thing that we can consider here is the fact that moment at this point, let us see in one of the elevation. As you can see, there is higher moment at the edges, so we provide hunches at this position, which looks something like this. So at the edges you can see we have hunches, so that helps in taking the care of the excess moment. That is, the use of the hunch reduces the required depth at rafter by increasing the moment resistance at that particular section where the applied moments are highest. And this hunch also adds a stiffness to the frame reducing the deflection. The length of these haunches is generally taken as 10% of the frame span. So now with this concept of moment about the minor axis, we can understand why we release the moment for this struts. So let me add a new window here, extruded view, and if we see here in the plan, right, so we have uh, struts, right, and we have I section as the column over here. And one thing you have to understand, so if this is an I section, the stress distribution will be something like this, with this being the compression and this being the tension. Now considering this as the moment, so this will be the stress distribution. The top flange and the bottom flange will be subjected to the maximum stress, and hence the flanges are taking the bending moment. So if you are trying to transfer the moment from beam to the column, they should be connected through the flanges. And on the other side, the wave takes most of the shear force, so it is simply that a simple connection with the wave is sufficient to take the shear force. And regarding the connection type used, whether it is a bolted or welded doesn't define that it is a moment connection or a pin connection. Here you can see it is a bolted connection and it is a moment connection. So for that, what we have to do is we have to make sure that there is no rotation at this point. If there is a rotation, then we cannot describe that as a fixed connection. Hence there we provide a restraint, that is we provide a stiffener plate so that there won't be any rotation, considering this as the flange, right? And as we said, at this point there is the maximum stress, and we provide a plate parallel to the flange so that there won't be any rotation. By stiffening this section, we can show that a level of fixity is achieved and it will be a moment connection. Also, another important thing that we have to consider for the portal frame, so for these raptors, as I said, we have purlins throughout it, right? So if you see in this, so this is the raptor and these are the purlins. So if we see here in the cross section, so we'll have a purlin at the top continuing throughout. So the top flange is restrained in position. So if it was under the dead load or this direction, this would have been the compression flange, but for now we are considering the wing load, so this will be the compression flange and it will be the most critical one, because under the loading it will try to buckle laterally. This is the lateral buckling. This is in case of the upward load, so this being the compression flange and this being the tension flange. And in our case it will be totally different, because the bottom flange will be the compression flange and the top flange will be the tension flange, and the tension flange is in position with the purlins. Hence, to keep the bottom flange in position, we provide fly braces. So these are the fly braces that has been used. So when a beam has closely spaced restraints which prevent lateral deflection of the critical flange and make sure that critical flange is the compression flange in case of simply supported, or and it will be the tension flange for a cantilever section, and that prevents, then this lateral restraint prevents lateral buckling, and the beam can be considered to have a full lateral restraint. Otherwise we have to consider the, like, we have to calculate the effective length of the segment of the beam and then consider the capacity of this section. Similarly, we also have these girts which can be considered as the lateral restraint for the columns. In addition to it, I would also like to make it clear about the position of the bracing. So that will be easy to understand with the loading. Let me show you here. For now, the wind load that we have done, we have applied. So if the wind is blowing from this direction, so because the bracing comes into play when the load is the wind is blowing from this direction. So with the distance from the first portal frame, the wind load coefficient at the roof decreases. That is, for example, the wind coefficient at the start will be 0 0.9, maybe minus 0 0.9, minus 0 0.9, and then at the mid span the wind coefficient reduces to 0 0.5, minus 0 0.5. So that means the central portal frames are subjected to lesser load due the wind action if it is blowing from this direction, as the central frame are subjected to lesser wind coefficient, and this is applicable only if the length along this direction is high. Because if it is considering three portal frames of this much span, that is 12 meter, that might not be the case, but in this case it is about 36 meter. So the influence of the wind coefficient or uplift will be less at the mid span, either case, if the wind is blowing from this face, or the wind is blowing from this face. So the bracing can be provided at this position, as this portal frame at this position is subjected to lesser uplift load. So now let us check for the frame section. Either we can do it manually or using softwares. So if you guys want to make a manual design of the sections, that is rafters, column, purlins, then do comment in the comment section. Now let us check with the steel frame design. So many of the members here are failing, so we need to increase the size. So I have changed the section sizes. So the columns here, those were ISMB 450, now I have changed them to 600, and the front portal frames will be the same, that is 450, but for the central one it will be 600 by 600, that is ISMB 600. The beam as well ISMB 600, and the braces that we have provided here are 100 by 100 by 4. So let us check now. Yep, so the section size is now okay. So what is the capacity here? 1.025, so that is acceptable for this one. Okay, so in this way we can design the portal frame, and I hope this video helped you, and if it did help, do like and comment in the video section, and